welcome to the 18th lecture. We started last time with Newton's law and then went to the rigid body dynamics. We will continue with that. So, if you remember that last time we have derived this relationship. So, and we saw that the extra term appears if we do not choose the point of reference in the body frame, or the body frame, if origin of the body frame is not located at the center of mass, then this extra term it appears, and this must be added, otherwise the whole calculation will be wrong. However, in most of the cases the origin of the origin of the body frame, it lies at the center of mass, and in that case, as this can be seen that for the rigid body we reduce it to this equation. This is for the rigid body, and if the origin of the body, this body frame which is indicated by E, this is body frame, and this we are taking as the inertial frame. So, if the origin of the body frame, if it is located at the center of mass, then rho c m will be 0. So, rho c m, this will be equal to 0 if the center of mass is located at, or if origin of the body frame, which we are writing as O, if O is located at the center of mass, and then this implies that m 0 or perhaps m 0 or m b we have written for this case. So, here m b it refers to the moment about this point, or either we write in terms of m o, and m o prime is the moment about this point. So, this gets reduced to d h 0 by d t, which forms our basic equation for the rigid body dynamics. Dynamics when the point O, and the center of mass coincide. Okay, so, there are various cases. We can see the topic we are presenting here, the same thing can be presented in numerous ways, and it differs from author to author. However, I will try here to present it in the simplest way, so that you do not face any difficulty. Many of the books, the material presented there, it is a very difficult to right away get into, but in this case I will keep the notations and everything very simple, and it will definitely get into your mind at the least effort. With the least effort you can get it. So, we continue with this. So, as we had in the previous figure, we have taken this. So, using this figure m 0 we are writing as d s 0 by d t. Now, if we put here the h 0, then we will get this m 0. Now, h 0, if this is the point O, and this is the point we have written as O prime, this is the E frame, and this is the capital E frame, inertial frame. Any point we have indicated this by rho I, and this distance from here to here by r 0, and then the h 0 we have written as delta m I, which is the mass times V I. So, this constitutes the this is your linear momentum of particle I, and this is h0. So, we are taking here in this case already we have taken the moment about this point. We took the angular momentum with respect to this point and then we have reduced to this form. Okay. So, we need not go back to this point again, now we can proceed with this. So, here we have to write this h0 is about this point. So, we need to write it this h0, you can refer back to the previous lectures. So, this h0 is rho I times delta m I times V I, where this is the distance and here your delta m I, the ITS particle of mass delta m I is located. Okay. Thus, and maybe this you can write as delta h0 to indicate this is for the small particle, and if you integrate it or sum it over. So, in the differential notation the same thing will be written by because we are not differentiating it, it is just one particle system. So, okay. So, we will continue with the summation notation, that will be the most easiest one to follow here. So, delta h0 and taking the summation over all the particles, and this is for the ITS particle. So, we need to put here the tag I also. Okay. So, this is the angular momentum of the ITS particle. Of the ITS particle about the point O. Here we have to be careful because we have eliminated this O prime already and we are working in terms of this point. Okay. And if we integrate it, so we get this as the this if we sum it up. So, we get this quantity here h 0 equal to rho I if we write it the same thing in the differential notation, purely in differential notation. So, the same thing we write here as rho is the distance of the particle, where delta m instead of writing here delta m will write in terms of d m. So, rho cross v d m, where v is the velocity of the this ITS particle we have taken here. So, this is v I. Okay. So, instead of v I we will write it as v, and then we need to integrate it. And this gives us h 0, because we have taken about the point O. And further this can be expanded as we know that this velocity of the point O will be v O plus rho dot, and integrate it over all the points, and this can be broken. Then we can write little bit with a better notation, rho d m cross v 0, because v 0 is not dependent on the mass integration, we are basically integrating it over the whole body. So, this integration is with respect to the mass. So, this can be taken out, or either we can write it like this. So, the other point, this will be rho cross rho dot So, you know this quantity, this is nothing but the location of the center of mass, and this quantity, this can be simplified further. So, it is a very easy, you do not need to memorize it. If you understand the physics, you will be able to write it. Okay. Only thing that we have to carry the notations properly, which frame we are working with. This we have arrived from the writing the equation about O prime. Okay. So, at least you need to understand that either we start from this place or either from this place we can reduce it to this point. Some of the books they directly start from this point, write the equation for the h and then keep on deriving the equation of motion, but we have started from this point. So, the this angular momentum of this particle we have written in terms of the absolute angular momentum, where r I we have written as r 0 plus rho I. And then we are reducing it to this format. Okay, so, we have now h 0 this equal to m times rho c m plus rho cross rho dot d m, and here one term is missing. We have here V 0 also cross V 0. Okay. Now, this term we have to look into, this is rho cross rho dot. Now, this rho dot, if you remember that while we have written d h 0 by d t plus V 0 cross p equal to m 0. So, at that time I have told you this derivative is with respect to the E frame, means the with respect to the inertial frame. So, here also while we are working with, as you look here in this place. So, though the distance is measured from this point, this rho I is from this point to this point. Okay. This is your rho vector. Okay, from here to here this is the rho I vector, but once you take the derivative, okay. So, this rho I variation, it has two components. One, it can be, say, this is a rigid body and there is a point here, okay, and the rigid body is rotating, but this length is not changing. Okay. So, the rho I in the inertial frame, obviously it will change. Okay, its orientation right now it is here in this direction, after some time it will be along this direction. Okay. So, as indicated by red line, after some time this rho I may go here in this direction. So, without change in length, this vector can change. Together with this, if this is a non-rigid body. So, in that case this distance from the point O to this point, it will keep changing with time. Okay. So, those two components, as we have written earlier, this rho dot with respect to the d rho by dt with respect to the E frame, this can be written as d rho by dt with respect to the E frame, or this is the body frame, plus omega cross rho. Okay. Means the rho dot which is appearing in this equation here, this is nothing but this quantity rho dot with respect to the E frame, and this can be written as rho dot with respect to the small E frame and plus omega cross rho. So, therefore, we can write this as rho cross rho dot with respect to the E frame plus omega cross rho, and then we have to integrate it. So, we get this quantity here. So, this will be rho d m cross rho dot with respect to the E frame plus rho cross omega cross rho Okay. So, this quantity, while we are working with this, so we have to do this in a particular way. This quantity, first we will look into this, what this quantity is. This is rho cross, we can write this quantity as rho dot rho times omega minus okay. So, this quantity is nothing but rho square omega minus okay. Now, we have two notations for this. One is called the dyadic notation, which we can follow, or in terms of dyadic, it says in terms of dyadic, and in the second one we can write in terms of matrix notation. Okay. So, this quantity we can write here as, I will come to this point what this quantity is exactly. The quantity that E double bar we have written, it is called the unit dyadic. First of all, a dyad is a product of two vectors. Like if we have vector E 1 and if we multiply it with vector E 2, so this constitutes a dyad. Similarly, E 1 cap, E 2 cap, this is also a dyad. So, here no consideration of dot or cross product, no consideration of cross or dot, we are not considering this. This is irrespective of the dot or cross. Okay. So, the unit dyadic, so and a dyadic is this is sum of dyads. Okay. So, you sum up two or more dyads, so that gets into a dyadic, and therefore, this E can be written as unit dyadic, it is written as E 1 cap, E 2 cap plus E 3 cap, E 3 cap. So, if you look into this now, if we take the dot product of this dyadic with this omega vector, so you can check this here E 1 cap plus okay. So, if we take the dot product, only the dot product between the similar vectors will survive, these are the unit vectors, and the dot product between E 1, E 2, E 1, E 3 they will vanish. So, we will get here omega 1 E 1, omega 2 E 2 plus omega 3 E 3. This implies that a unit dyadic leaves the vector as it is. If you take the dot product of a vector with unit dyadic, it leaves the vector as it is, it does not change it. Similarly, the vector appearing there, this is rho rho, this is also a dyadic. Because it is a product of two vectors. Now, this rho you can write as rho 1 times E 1 cap, these are expressed in the body components, rho 2 times E 2 cap, rho 3 times E 3 cap, and then multiply it with rho 1 E 1 Okay. So, here in this case what we see that if we multiply it. So, this will be something like rho 1 square E 1 cap, E 1 cap and so on the other terms. So, we did not expand it here right now. Now, going back to this equation. So, therefore, this equation can be written as rho square E double bar minus okay. So, rho square E double bar minus rho rho dot omega. So, what we get there? Rho square E double bar dot omega, and this we are integrating over the term d m. So, this omega it does not depend on the mass, okay. This is not over the mass. So, this is the rotation rate of the frame which is fixed in the body. So, what we can do that we can take it outside rho square integrate it over the body and this dot omega. So, we can represent something like this, and the quantity which is present here, this is written as I double bar, and this quantity is called the inertia dyadic. Now, again picking up this equation, okay. We consider this equation rho square omega minus rho rho dot omega, and this is integrated over d m. So, we have this is rho square omega minus rho dot omega and d m. This is the integration we are looking for. Okay. So, this integration can also be represented like this. We can write rho square and this omega we can write here the unit matrix, and unit matrix I will represent it like this, or the identity matrix. Okay. So, this is I times omega, this does not change. This say although a proper way will be to first convert this into the this vector into the matrix, for converting this vector into the matrix notation, we can refer to the vectrix, but rather than writing it like this, you can, because that will just take more time to do the same problem. Rather than writing it like this, you can consider that this omega is nothing but omega 1, omega 2, omega 3. Okay. So, either if you write in matrix format, you will write like this, and if you write it in the vector format, you will write it like this. So, in the matrix format, this is your identity matrix. Okay. And this is omega minus, now you know that the quantity from here to here, okay, rho times rho dot, there is a dot also. So, if you refer back to our lecture earlier, so this we have written as rho tilde transpose, okay, rho times rho dot, this we have written as this quantity, and we have proved this also. And therefore, what remains there, this is omega tilde, and this omega also omega which is coming in the vector notation. So, that we will change to tilde. So, this removes the unnecessary work in terms of the vectrix, and this is the same thing. So, quickly from your exam point of view or while you are working, so you can quickly go between this and this without considering the vectrix. Now, look into this quantity, we can take out this omega outside, and this is nothing but a matrix. So, if you look into this quantity rho a square rho square is a scalar, and what this quantity is, here this is transpose. So, this turns out to be a symmetric matrix. So, here basically you have rho square, rho square, rho square 0 0 minus, and then you have rho 1, rho 2, rho 3, rho 1, rho 2, rho 3. So, and this turns out to be a symmetric matrix, this also symmetric matrix, this is also symmetric matrix. So, this says that these two together which we have represented here, it forms a symmetric matrix, and we can write this as. So, what we get from this place, if we expand it and write it, so this will be rho square minus rho 1 square, the first term, the second term is here 0 here. So, only thing that will enter from this place, which is rho 1 rho 2 with minus sign, then similarly rho 1 rho 3. Okay. So, this quantity indicates that this is equal to this value with minus sign. Similarly, here rho 2 times rho 1 with minus sign. So, this is rho 1 rho 2 with minus sign. This one again, this is rho square minus the middle term, which will come to be rho 2 rho 2 rho 2 square, and then this is rho 2 times rho 3 with minus sign. Okay. Similarly, we have the rho 3 rho 1 with minus sign, then rho 2 rho 3 minus sign, then rho square minus rho 3 square. And this term, if you further simplify, so rho square minus rho 1 square, you know this will be equal to rho 2 square plus rho 3 square, and then the rest of the terms here we can write rho 2 rho 3 rho 1 rho 2 and then minus rho 2 rho 3, this is in the matrix format. Similarly, here minus rho 1 rho 2, this will be here rho 2 we are subtracting. So, we get here rho 1 square plus rho 3 square. Okay. And similarly, this place which is rho 2, this is rho 1 times rho 3, rho 2 times rho 3 with minus sign, rho 1 rho 3 with minus sign, rho 2 rho 3 with minus sign, and here it comes to be rho 2 square plus rho 2 square plus rho 2 square plus rho 1 square. So, this quantity gets reduced to this, and next we need to integrate it 5, and next page we have 6. So, rho square times I minus rho times rho transpose d m. So, if you integrate it, means the whole matrix we have to copy it here and integrate it. Okay. So, the first term after integration that we will get. So, this will result in I 1 1, the next term we can write as I 1 2, I 1 3, I 1 2 or I 2 1, whatever you want to write, because it is the same. Okay. Both of them involves rho 1 and rho 2. So, it is the same, or maybe let us write here I 2 1 to be more formal, I 3 1, I 3 2, I 3 3. So, that means this term what we get here, this is called the inertia matrix. The same thing we have written in terms of inertia dyadic. Okay. So, now going back here, if you look into this, this we have written as inertia matrix. So, if you write the same thing in terms of the matrix notation, so the same thing can be reduced to, this is equivalent to writing it I times omega tilde. Okay. So, this is your inertia matrix, and this multiplied by omega, that gives you the h value, one term of the h that we have been writing. So, we will continue in the next lecture. Thank you very much.